Good evening, everyone. So, I am Rakesh, a doctoral student at IIT Bombay. So, I am also a PMR fellow. So, I'll be taking the live sessions on manufacturing process and casting joining course, which is excellently taught by Professor Sonukumar Chaudhary from IIT Kanpur. So, this live session will run every Saturday from 6 to 7 p.m. So you are most welcome to join, and please join earlier so that there will be no obstructions in the middle of the class. So with that, I will so in this lecture I will just explain some couple of numericals that will be helpful for you to solve your assignments, and the further session, live session also will be useful for you to attempt the assignments with ease. So without any further ado, I would like to start the session. So I would like to explain each and every question, and I will also explain why the options are wrong and which option is correct and why it is. So if you see in the first question, so it is like in die casting process, the mold material is sand and the molten metal is in die casting process. They are given some 4 options. So the first option is the mold material is sand and the molten metal is poured by pressure. First of all, you can see it is a die casting process. So you have already seen in the lectures. So die casting process is mainly used for low melting point metals, and directly we will use metal as the material for the mold. So the first option he is saying is like the mold material is sand, which is an incorrect statement. So from that we can neglect that first option. So the second option is the mold material is metal. Yeah, that is true. And the molten metal is poured by pressure. Yes, that statement is also true. So correct option is B. And the third option is the mold material is metal and molten metal is poured by gravity. Yeah, this statement seems a bit true to the half. So the mold material is metal. To that thing it is correct, but the molten metal is not being poured by the gravity. It is poured by pressure. I will explain why it is after explaining seeing the fourth option. So the fourth option is the mold material is sand and the molten metal is poured by gravity. So the mold material is not sand. So this option is incorrect. So now coming to the option 3. So yes, it is true, you can use gravity, but we generally use this die casting process for a mass production. So if you use gravity, the main motive of designing die casting will be lost. So what happens in metal die casting? So we generally use high pressure die casting, so in which if there are intricate shapes which are very thin. So what happens with gravity, the metal may not flow into those intricate shapes. So we have to use some pressure to push the metal into that very constricted passages. So that's why we have to use pressure. And one more thing is that, so with this pressure, what happens? The time for production of any single object will be reduced. With gravity, we cannot produce a mass production very quick. The time for the production time, or the preparation of the object time will be very high in gravity casting. So that's why we use some pressure so that the part will be over within like 1 minute. So the main motto of designing die casting is to quicker the process as well as improve the flowability of the metal by using some external pressure. So that's the main motto of die casting. So the option 2 is the main appropriate for this question. So I have shown you some picture here, which I have taken from this NPTEL course. So if you see that car doors, it is manufactured by, say, stamping process, or some of the parts inside the car which are manufactured by this high pressure die casting. So the engine parts, engine blocks, so which are very small in size. For the big blocks we go for gravity, but there are the small shapes which are intricate in design. So in that process we will use this die casting process. Now coming to the option 2. Now coming to the question number 2. So in casting, so before going to question number 2, So the first question, which is about, is testing your knowledge on die casting process. The question is all about die casting process. In the second question, they are testing us in the sand casting process. So in sand casting process, the first option is expendable mold is used. Second option is the permanent mold is used. Third option is the molten metal is poured by pressure, and the fourth option is the part can be produced to net shape. So let me come from bottom. So the part can be produced to net shape. It is not true. In sand casting, the surface finish of the object or the product we produce, it is not so good when compared with the other machining processes. So that statement is wrong. Next, the molten metal is poured by pressure. It is also wrong, because in sand casting we use sand as the mold as the preparation material for the mold. So if you use some pressure, what happens? The sand cannot withstand that much of pressure. It does not have that much strength to withstand, and we never use pressure in sand casting process, of course. So that is not the correct option. Now going to the option number 2, a permanent mold is used, which is wrong. So in sand casting, once the metal is poured into the cavity, immediately it was broken down, and all the sand is reused again. So the mold is not permanent; it is collapsible mold. So that is not wrong. That is wrong. And the option 1 is the correct one, because the expendable mold is used, because every time the mold is broken down and it is reused. So we will not keeping the mold constant for all the process. So the option A is the correct option. The next question. So the second question that we discussed earlier, it mainly focuses on sand casting process. Now let us coming to question number 3. A pattern is, it's a mirror. So the pattern, I hope you guys know about the pattern. It was the object that is used to prepare the mold cavity, and later it was taken. There are several types of patterns also. So that is the main goal of using this pattern. Now let us see the option. The mirror image of the part to be cast. No, it's not the mirror image of the part to be cast. It is not the mirror image. The second option, an element in casting process used to compensate for shrinkage. Yes, true, but that is not the main motto of using pattern. So we'll keep aside this option. Next option is an element used to make internal holes in casting. We have a special name for that, which is core, that we use for giving internal cavities for an object. So the option is wrong. Now coming to the option number 4, the replica of the part to be cast. Yes, this is the correct appropriate answer to this. It's the best definition for the pattern. It was the replica of the cast to be produced. Now coming to the option number 2, an element in casting process used to compensate for shrinkage. So basically we have 3 types of shrinkage. So one is liquid shrinkage, the second one is liquid to solid shrinkage, the third one is solid shrinkage. So what happens is that this liquid shrinkage or liquid to solid shrinkage can be compensated using riser. Only the solid shrinkage, and it is very less, which will be compensated using this pattern. So this option is not specific to what shrinkage it is being compensated. So we cannot exactly take this option as the correct option. So the option number 4 is the appropriate for this question. So going ahead, so a patterns are made somewhat larger than final job to be proceed. Yes, that is true. This excess in dimension is referred as. Yes, the patterns in general, I have also explained you earlier that the surface finish for the cast product is not so good. So what have I to do? We have to do some trimming process and some finishing processes using some machining objects. So we will provide some extra dimension for that. So that extra dimension is called allowance. It is not the tolerance, and it is not for the casting defect, and it is not the draft. So I will explain draft in the coming questions. So what happens, this allowance consists of 2 things. So I have explained earlier. So in pattern, the one is the shrinkage allowance. With shrinkage, solid shrinkage or solid to liquid a bit, and the second one is the machining allowance. So this machining allowance and the shrinkage allowance, it's a combined allowance. These are the two parts in allowances. Tolerance is not the term that we use here. We use allowance here. So that is the correct option in this. And let us move to the next question. Yes. So this question is completely about shrinkage allowance. So I have taken the formula from the lecture notes. So let us read one by one. It's a lengthy question. So first option is, it is about shrinkage allowances. Is directly proportional to the linear coefficient of thermal expansion of the material. Yes. By what? Just by remembering the formula of shrinkage allowance, the first term alpha L is the linear thermal expansion coefficient, and next L is the length of the casting, and theta F is the freezing point temperature, and theta naught is the ambient temperature. So it depends upon all these parameters. So the first option is directly proportional to the linear coefficient thermal expansion. Yes, true. So now go to the options. You can see option A and option C are consisting of these option 1. So we can eliminate the option B and C. So this is how we approach if the question is lengthy, so that you can save some time in the exams. The second option is inversely proportional to the length of the castings. No, it is not inversely proportional. It is directly proportional to the length of the casting, as you see in our shrinkage formula here. So option 2 is wrong. So if you see option A and B, there is no option 2. So we have to go for the next option. Does not depend on the ambient temperature. No, it is wrong, because it will depend upon the ambient temperature, because there is theta naught in the formula. So option 3 is also wrong. So if you see, option 3 is also not there. So option 4 is the deciding one. So now if you see, is directly proportional to the freezing point of the material. Yes, that is the correct option. It is directly proportional to the freezing point. So now actually the session is not someone joined right now, so I will continue some questions. If you have any doubts, I can answer you at the end. So actually there was session yesterday, but there was some problem with the recording, so again I'm taking the session today. So you can be listen to there were around 10 questions. You can listen till then, and you can ask if you have any doubts. So I'm explaining question number 5th. It is almost completed. So if you see option number 5, it does not depend on the length of the casting, which is wrong. So because it will depend upon the length of the casting. So the correct option is 1 and 5. Sorry, does not depend on the length. Sorry, it will depend upon the. So the 5th option is wrong. So the first option you can strike off. So the correct option is option C, 1 and 4. So that is being said, I will move on to the next question. So it was a numerical based upon this shrinkage. So you have to remember this formula, shrinkage formula, to answer this question, because if you see, there is no quadratic term in the formula. Everything is linear. So if you are comparing, if there are two objects of same material, you can directly compare it. So if you see question number 6, so there are two castings A and B, which are of same material under the same conditions. So the ambient conditions and everything are same. So now the casting A is 1.5 times in length than the casting B. So we can note down that. So casting A is 1.5 times casting B. This is the length. Or else you can clearly write like this. Length of A is 1.5 times the length of B. Okay. Next, the shrinkage allowance in A is given as 3 mm. The shrinkage allowance in B will be. So it is directly we can equate this. So now if I say shrinkage allowance in casting A is 3 mm. So now they are asking shrinkage allowance in casting B. So we just need the this constant, that is 1.5, because that is what, because it is a directly linear function. So we can directly divide by that. Shrinkage allowance of B is equal to 3 divided by 1.5, that is 2 mm, because the shrinkage allowance is directly proportional to the length. So we can directly, if there are two objects of same material and same conditions, so we can directly erase shrinkage allowance by length of the casting is constant. So by using this formula, shrinkage allowance of A by length of A is equal to shrinkage allowance of B divided by length of B. So this is how I solved here. So the correct answer is 2 mm. So similarly, you can we can play with this formula and we can get the answers similarly. So moving on, there is question number 7. So a taper put on the surface parallel to the direction of withdrawal of the pattern from the mold cavity is refers to as. So this was the direct question that is being answered, that is being asked. So what happens if there are any straight edges? Suppose, assume this is the hatched part is the mold and this is our casting. So what happens if you have pattern like this, if you want to remove these things, even if a small disturbance while removing will damage the sides of the casting. So to avoid that, what we will do is we will give some small taper for the pattern to remove. So now it will be easy while removing. It will be very easy. Even if there is a small difference, it will not much affect the casting slides. So that's why we'll give some small taper. This taper is very less. Will be like erode from 0.5 degree to 2 degrees. So very small taper. So it is like the understanding between the customer and the company, so casting company. So if the customer is okay with this small taper, it is fine. But if he does not need the taper, so finally we have to machine out this extra surface. But it is useful for us, even if it has adding some, it will not damage the dimensionality. So even in daily uses, mostly in railway stations, if there is any construction, if you see that bars, they will have some small taper. It will not much affect the functionality, so they will not trim it out. They will directly use it. So if you again visit, if there is any construction in a railway station, you can keep this in mind and you can see it is very beautiful thing to observe. Yeah. Going on. So a turbulent flow of metal into the mold should be avoided since it is. So this was an interesting question which tests on the gating design and gating systems. If you well understand this gating design and systems, you can easily answer this question. So in gating design, we don't want turbulent flow. Every time we want a laminar flow in it. So we have to, at any cost, we should not allow this turbulent flow. So if you go on seeing the questions answers. So the first option is accelerates the formation of oxide in the solidified metal. Yes, if there is a very high stirring or very high turbulence while pouring into it, it will attract the oxides, and the oxides will be inside the casting, and it is detrimental for the casting. So that option is correct. So if you see the option A and B have this first option as their selection, so we can directly neglect option B and C. Now see, we can directly go to option 4 or option 5 and options. So I can directly go. So if I go to option 5, I can directly decide the factor whether they are true or not. So if I go to the option 5, sorry, it causes the mold erosion. Yes, true, it causes the mold erosion. That is true option, and it is not there in option A, so I can neglect this. So the correct option is 1 and 5. So this is the way you can answer, but let us see the other options also to understand. So second thing is that violates continuity law. No, it does not violate continuity law. It will obey the continuity law because it is depend upon the conservation of energy. So next, option 3 is causes thermal deformation of the mold. No, it will not causes any thermal deformation, because we design the mold in such a way that it should not. So it will, the turbulent flow will not induce any deformations. That is wrong. Causes the formation of gases. So there was some discussion yesterday on this also. Causes formation of gases. In general, what happens? Hydrogen and nitrogen, these are the two gases that are mostly the culprits in the castings. Mostly it will be absorbed or it will be trapped in the liquid. So the liquid have more solubility when compared to solid, so it will come out during the solidification, and it will cause the defects. So say the pinhole defects or gas porosity. So it will not form any gases. This turbulent flow will not form any gases. It may attract the gases from the other side. Suppose if I am using sand casting, it has very good permeability. So what happens? The outer atmosphere air can enter if there is any low pressure inside the casting. So it may attract the gases, but it will not release any gases. It will not leads to any formation of gases until there is any chemical reaction going in the liquid stage. So the turbulent flow will not cause any formation of gases. So that is wrong option. So fifth option we have discussed, and sixth option is completely wrong. So the correct option is 1 and 5. So next question is that the aspiration effect can be eliminated by designing. So as I explained earlier, so what is this aspiration effect is? So if we have any mold which is made of sand, it will have some permeability, means the gas can enter inside. So because the sand particles are like this, there will be some small gap in which the air can enter. We have this permeability index, permeability value also. So if you have any casting inside, a sand mold, what happens when you pour any liquid? If there is any low pressure generating inside, it will attract the gases from outside. So this leads to the formation of defects in the castings, or it will leads to the say some low it will lead to some liquid turbulence inside the casting. So that's the main defect that is being explained here. So it is known as the aspiration effect. So while designing this gating system, we always have to ensure that there is no low pressure being generated in the casting. So this can be ensured. So there are two things we have to keep in mind to avoid this aspiration effect. So one is the designing of sprue, and the second is any change in cross sections, change in fluid direction. So the first option is like the sprue design. So the sprue design should be tapered rather than the cylindrical. So I will derive some small derivation to explain this concept, sprue concept. So I will explain the fluid direction. So suppose we are having the liquid is coming in this direction and it is going to the right direction. So what happens? The liquid will initially make this path. So this is called a vena contracta. So we are having this area which is low pressure area. So we can expect some air to be entering in that area, and it may cause defects in castings. So this we can take care by designing that design of that sprue. We can provide some material like this. If you follow the fluid path, there will be no chances of this aspiration effect. So we always have to allow the fluid. We have to follow the path of fluid. We should not restrict it, so that we'll get a good sound casting. So now going to the options. The sprue is in cylindrical shape. Yeah, we can, but it is not the ideal shape. So I will keep it aside. Next option is the riser volume to area ratio more than casting. So aspiration effect is nothing to do with the riser volume. So we can neglect. The riser is in taper shape. We don't need that. It is not related to riser. So the fourth option is the sprue is in taper shape. Yeah, that is the correct option. The sprue should be in taper shape. So one simple example I would like to give, the flow path. So if you have any tap, so if water is coming, sorry for this wrong diagram. So water is coming and water is flowing here. So if you see this is the path how the water follows. Initially the cross section will be more, while coming to the cross section is more because the velocity increases, so the area should decrease to maintain discharge constant. Here the velocity will be less but area will be more, so that the discharge is constant. So this is the actual path that is being followed by water. If you see, if you open the lid without any turbulence in it, it should be laminar flow. This is what the shape is, like the taper shape. It is not the cylindrical shape. So this is very simple example I am giving to remember the shape of sprue. It should be tapered always. It should not be cylindrical shape. So the correct option is option 4. So this sprue concept I will explain after this numerical. So this numerical is asking us about the gating design and the velocities at each and every point. So basically we can directly derive this, and we can, or else we can remember. This is a simple application of Bernoulli's principle between any 2 points. So the question is, the sprue leading into the runner of a certain mold has length 175 mm. So I have taken this diagram from the presentation, which is from the Amitabh Ghosh and Maulik textbook. So now the sprue height is given 175 mm. So we have to keep an eye on this units. The velocity of the molten metal flowing to the base of the sprue is. So they are asking velocity at 0.3, and let us assume this is the height, that is 175 mm. So if you apply Bernoulli's principle from 1 and 3, between 1 and 3, so we have to take P1 equal to V3 as atmospheric, and V1 is equal to 0, and H1 is equal to 0. So V3 we should find, and H3 we have value with the value we have. So if you apply Bernoulli's principle from 1 and 3, we will get the solution as V3 is equal to square root of 2gH3. So that is nothing but 2 into. So I am taking the answer. If you see the answer, they are asking in mm per second. So we have to keep everything in mm per second. So they have given the value of acceleration due to gravity also in mm per second square. So 2 into 9815 into 175. Take the square root. So directly we will get the answer in mm per second. You can check the answer. The answer is 1853. Yeah, this is very simple and numerical. So there will be a numerical on filling time also, which you can easily calculate using this discharge formula. So I will explain the discharge that thing here. So we have discharge is equal to meter cube per second. Say meter cube volume of the casting I am taking per time t. So this time is the filling time. This is also equal to area into volume of the sprue. So now time of filling is equal to volume of the casting divided by area into volume of the sprue. So that is nothing but volume of the casting divided by area of the sprue into square root of 2gH3. This is the simple numerical that might be asked in the exam. What is the filling time and what is the pouring time? It is a famous question in interviews also. So now I will there was so much discussions on aspiration effect, so I will explain this aspiration effect and why we need the sprue shape as a taper and why not cylindrical. So there is very good explanation in Amitabh Ghosh and Maulik textbook also. So that difference you can take to understand this concept. So now let us take a cylindrical and sprue. I am taking this as figure 1 and this as figure 2. So I have points. So this is pouring basin 1 point 1 2 3. Similarly, I have a pouring basin here also, 1 2 3. So now I will take the cylindrical, and I will see why it should not be used. So the main goal of our is that no aspiration effect, that is pressure should not be less than atmospheric. Pressure should not be a vacuum, there should not be any vacuum, because if there is vacuum, it may entrap gases inside, it may trap the gases inside. So now initially I will take the cylindrical. Now I will take the cylindrical one, and I will see. So if I apply Bernoulli's principle between 0.2 and 0.3, so if you see Bernoulli's principle, G into H2 plus P2 by metal density plus V2 square by 2 is equal to P3 by metal density plus V3 square by 2. So now the P3, so in ideal case, if I am taking, so this is the critical point. P3 is the critical point, because at 1 we have atmospheric pressure density, and 2 also more or less we can, but at 3 it is inside the mode, which should not be a vacuum, or it should not be negative pressure. So in ideal case, what I am taking is that I am taking P3 as 0. So there is no pressure at in ideal case. It should be atmospheric pressure. So now I can determine what should be the pressure at P2. So if you see, and the velocity at V2 and V3 should not be changed. So that is also one concept. So the velocity should be constant. V2 should be equal to V3, because there should not be any disturbance. It should be linear. It should be lambda. Sorry. So now we can see that P2 is equal to minus GH2 rho m GH2, which is negative. So which is not acceptable in our case. There should not be any negative pressure at point 2. It should be a turbulent flow. It should be a laminar flow without any. This is happening because it is a cylindrical sprue. We are not following the shape of the fluid flow. Now see, if we apply same formula for sprue, and let us examine that thing also. So now for limiting case, what should be think is that the P2 pressure also should be atmospheric. So P2 should be 0. So case 2, I am taking limiting. So it is like the equal to atmospheric, or it should be greater than. So limiting is that it should not be negative. So I am taking pressure as 0, which is the limiting case. So now what happens? So if I apply, say similarly, if I apply now apply same boundary conditions. So this is what happens when P2 is also equal to 0. Now the velocities are not equal. Previously, if you follow the continuity equation, A1 V1 equal to A2 V3, and area is constant. So in this case, since area is constant, so we have V2 V3 equal V3 because the discharge is same. So but here the velocities are not equal. I'm taking, because it is sprue shape, the velocity, the area is changing from point 2 to 3. The velocities are not constant in this case. So now let us denote it as equation number 2. So now if we apply continuity, A2 V2 is equal to A3 V3. So from this, V2 is equal to A3 divided by A2 into V3. Let me denote this area ratio with capital R. and denote this equation as equation number 3. So what I did is I have applied the continuity equation between point 2 and 3, and I have got a relation between V2 and V3. That is it is like the ratio of the area. So now from equation 2 and 3, we have V3 squared by 2 is equal to GH2 plus R squared V3 squared by 2. So if we simplify this, we will get value of R 1 minus. So this is the value. So therefore R is equal to, so before going to this R directly, now see, again we know that V3 square is equal to 2Z into total height of the casting. So that if you substitute that thing in here, so we will get 1 by H2 by HT. R square is equal, that is equal to the ratio of A3 by A2 whole square. So the final so here I will write, the final equation is R is equal to, it is the ratio of A3 by A2 it is also equal to HC by HT. So this is the height of the casting and it is the total height. So if you do this some simplification, you will get this answer. So if you see, the ratio between areas is not linear with respect to height, it is the some function, not non-linear function. So this is how we can get the limiting case of pressure equal to 2. So if I have done this example to show you that the areas are not varying linearly, so the areas at 2 and 3 they are not same, they are instead they are varying with respect to height. So this is simple derivation that we can do ourselves, very simple derivation to understand this concept of design of the sprue. So this I want to explain because there were so many doubts on this, why we have to take sprue and why not the shape of the sprue as this shape of taper, or why not the cylindrical. So actually the shape it is not actually the taper also, but we generally follow, if for our in study purpose we do this, but actually the flow will be very this kind of design. This is the actual, but for our in generally what they will do, this is the very ideal the practical one that we use in our casting designs. So this was very beautifully explained in this Koshan Malik textbook also. You can go and derive yourself also. It is very simple application of the Bernoulli's principle. So we can get the relation between the areas and how the areas are varying with respect to height. So this is being explained, and I have, if there are any questions or if there are any doubts regarding all these questions, you can definitely ask me in the next session, and I will make a note of it and I can explain you. So there was one more question on how many degrees we have to keep the taper. So I have seen somewhere the taper angle is very less, it is below 3 degrees. Also it depends upon the actual industry practice. So in general they are using 3 degrees. of taper in general they are using for this casting purposes. So, and the shrinkage dependency also there was question, what is the general values? So in general shrinkage mainly depends upon this say the cooling rate, how you are cooling it, faster cooling rate, slower cooling rate, it depends upon that, it and how the riser position is being provided everywhere. So the riser should be the location of riser should be well known in order to avoid these shrinkage defects. But by any chance we should not allow this turbulent flow into the while pouring the liquid metal into the casting. It should be laminar in actual practice. And there was one question on cold shed. What is this cold shed defect in castings? So I will explain that concept, that definition. So what happens in general, if you have a casting, say I'm having a hollow, I have a cavity at the center. Now see, if the liquid metal is coming, so initially say it is falling like this, and it is filling, and meanwhile there is also a liquid stream entering like this. So if there are simultaneously entering in this, somewhere here, somewhere here, depends upon how pouring is done. So the two liquid streams, this is liquid stream 1 and this is liquid stream 2. If the two liquids are meeting, because of this difference in those cooling rates, we can see one small appearance of crack, because they are not fused well, because of lack of the cooling, because lack of the availability of heat for them to combine or form a seamless design. Seamless. So we can see these casting defects mostly on hubs. So if you see hubs like this, so now see, so now the fluid enters in this way and the fluid enters in this way. Somewhere you will get the crack appearance. So this is called cold shed defect. So it does not have enough heat content in it to freeze and form a seamless casting. So this appearance of this crack is known as cold shed. We can eliminate by providing some small risers in this design, or one way of doing it is providing riser. The other way is that we can increase the pouring temperature or the preheat that is being for the liquid, so it will have enough content to freeze, form a seamless design, seamless bond in the casting. So this is one nice question. So this will be taught in future classes, the defects of casting. There are so many defects that will easily explained in this. So this is one interesting questions that was being discussed. And if there are any doubts on this week 1 sessions, please do ask in the next live session, which is being conducted on Saturday, every Saturday, and I will be happy to help. If not, I can note down your queries and I can answer you. Please do attend this session so that it will be easy for you to attempt all the assignments, because most of the questions that I explained here are very closely related to the assignment questions. So it will be easy for you, and it will not be a regular sessions. Instead, it will be very interactive sessions. So please do join early so that you can get a good explanation from me. Yeah, thank you. So if there are any questions, you can ask, or we can end the session. Thank you. Yeah. So the aspiration effect can be eliminated by the designing. So this aspiration effect mainly depend upon the shape of the sprue. So here we are interested in what type of shape should we use. So the first one is the cylindrical shape, and the fourth option is the sprue taper shape. The middle B and C is related to riser, which are neglected. So between cylindrical and taper, so taper is most preferred. So I have explained here, because the velocity we have when we have some head. So at point 2 we have some head here. So what happens, the velocity will increase very high. As well, while pouring, what happens, we will get this in if you see the second cylindrical shape, we have the flow suppression. The flow suppression happens. So that's why we will prefer the taper shape more when compared with the cylindrical. So one thing is that we have to minimize this velocity at point 2. The second one is that we have to remove this flow suppression. If the flow suppression happens, there is a problem of aspiration. So there the air may get trapped inside the metal.
Yes, sir.
Yeah. Thanks. Yeah. Is there any other doubts?
Thank you, sir. Have a good day, sir.
Yeah. Thank you. Thanks for attending.
Sir, can you explain aspiration effect?
Yeah. I just explained. So what happens is that when we pour the metal into the sprue, so if the design of the sprue is not so good, what happens? The air, if the velocity, if the pressure inside that sprue is less than the atmospheric pressure, so the air get trapped inside it. So in the cylindrical shape, if you see, there is a flow separation here. So if at all the flow gets separated, there is a chance of formation of eddies inside, and it will the pressure inside that will be very below the atmospheric pressure, and which leads to trapment of gases. Is that clear?
Yes, sir. Thank you, sir. Have a nice day.
Yeah. Thank you.
Will leave now, sir?
Yeah. Yeah. You can leave. If you have any doubts, you can stay. Otherwise, you can leave. Guys, if you have any doubts, you can ask. Otherwise, you can carry on with your as usual work. So, so the cold shut occurs. So there was one question: in which cases defects like cold shut occurs? So cold shut occurs if the riser design is not so good. So if the freezing point, if we didn't design the gating system or the casting with the if it within the range of freezing. So what happens is that, so the cold shut effect is more predominant in forging. As well here also. Suppose we have this is the casting, and we have say one more casting inside. So this is what the casting product I need with the cavity at center. What happens is that when the liquid enters, so it will feel like this, and it will feel like this. It will go. At the end, what happens if the either of the side are solidified before completely filling, so we can see one crack formation at the center. So this defect is like what we call cold shut defect. So if it predominantly solidifies, the two friends are meeting at the same time, and there is no chance for them to combine completely, so they will solidify independently. So this defect we can call as cold shut effect, and this is very predominant in forging as well as in casting also.
Sir, how can we compensate, sir, this defect?
So it is very simple. So what we have to do is we have to build a small riser here. just design one small riser on behind the front. So what happens when they combine the when they try to combine, the riser will provide the liquid inside. So these are the spots that we expect. So before finally designing, we will do some small run. So when we find this, we can before that also we can identify the location of this riser, and we can we can avoid this type of defects.
Okay, sir. Thank you.
Yeah. So, is there any doubts?
सर मैं हिंदी में बात कर सकता हूँ क्या?
What?
Can I use Hindi, sir?
I'm comfortable in English, but you can speak Hindi also.
Sir, during solidification, sir, every metal have different solidification rate, and sir, shrinkage also happens in during this. So, can you explain the shrinkage series, sir, for every metal? Which metal have कौन से metal के पास ज़्यादा shrinkage हो सकता है, कौन से metal कम shrinkage हो सकते हैं sir during solidification?
Yeah, this can be. So I don't have actual data with me right now, but this is true. It depends on the metal also, and it also mostly defects on the cooling rate. So what type of cooling rate we are providing. So these shrinkages, solidification shrinkages. So we have three types of shrinkages. So one is the liquid, the second one is the solid liquid transition shrinkage, and third is the solid shrinkage. So this solid shrinkage can be avoided using this say the pattern design. So what happens in liquid and solid liquid transition shrinkages, we have this gas shrinkage and we have this liquid shrinkage. So this gas shrinkage we can avoid by degassing it, or by avoiding keeping the riser at certain portion that the gas will finally settle in the riser. But this solidification shrinkage occurs. This is also depend upon the riser also. So what happens while if there is in casting, when you pour the metal inside, there will be some hot spots. So where the everything will solidify at that center at that point. So what happens during shrinkages? So if I take one big casting here, what happens at the center? So we have cooling from this side. We have cooling from this side. We have cooling from this side. So at the center we have. So what happens? All these solidify first. So what happens when it comes to the center? There is no liquid to feed this shrinkage. So we'll get the shrinkage at the center if all the sides are cooled equally. So this is how the shrinkage is depend upon the cooling rate. This cooling rate. So this is one of the main factor. Then comes to the metals.
Sir.
It depends upon the materials. Yeah. Ask.
Yes, sir.
Yeah, someone is asking some question. Is there any questions? Someone just joined. So this video will be uploaded in YouTube. You can check with, and you can come back if you have any questions in the next live session at the same time.
Sir, this video will be available on YouTube.
Yes. This video will be available on YouTube. You will get a notification soon.
Okay, sir. Thank you, sir.
Yeah. Please do join at 6 o'clock so that we can have some live interaction. Yeah, thank you.
Thank you, sir, and have a nice day.
Yeah, thank you, Ashish. So if you have no doubts, you can leave. If you have any doubts, you can ask.
Okay, sir. Okay. About the practice questions, sir,
Yeah.
exam related.
Can you repeat your question? Actually, there was some lag.
Sir, I'm saying that what about the sir practice questions for exam, sir?
So you can practice these assignment questions mostly. Then comes to, yeah, assignment you solve first. Then you can go through the slides that the professor presented.
Okay, sir.
That is more than enough. So there was sir is professor is presenting in a very nice way. So if you are so watch the complete video so that you can get very good grip on these subjects.
Okay, sir.
Okay, we can. If you have no doubts, I can close the session.
Okay, sir. Thank you, sir.
Yeah, yeah.